Alright, welcome everyone to today's lesson on how to build a rocket. So today we're starting off with step 1, which is simulating your rocket in Openrocket, also known as Openrocket Design. As a reminder, an L1 stands for Level 1 rocket. It's your first step to getting high power certified. So, just as a bit of a refresher, what is an L1 rocket? There's a link to the requirements in the presentation, which you'll be able to access and take a look at that. But essentially, it's a rocket that flies on an H or I class motor. It needs to go up, deploy a parachute, come down, and land in a good enough condition that you could theoretically fly it again with nothing but minor repairs. Now, there's a few key areas of the rocket. First of all is the nose cone. It goes at the top. It's pointy or rounded. It helps the rocket sort of punch through the air. Then there's the body tube, this main part of the rocket right here. That is essentially the airframe of the rocket, the main structure of the rocket, and it's hollow, so the parachutes and the motor fit inside there. And that's what we sort of glue everything to as we build the rocket. Then there's the fin assembly, which you can see the fins sticking out, but they really go in through the cardboard tube and inside there, and that's how they hold the motor together and provide really good, strong stability for the fins. Then the parachute goes inside the rocket. You can't see it here, obviously, because the rocket is opaque. And finally, the motor goes in the bottom. Flame comes out the bottom, rocket shoots up the rail and goes into the sky. So, there are quite a few steps in the process for designing and building an L1 rocket. Today we'll be talking about the Openrocket design, like I mentioned. So, just a little bit about Openrocket. It's the main entry-level simulation software for any rocket. And the goal with using the software is to get a layout of our rocket and to make sure that our rocket will be stable when it flies. Now, why is this important? Well, when our rocket isn't stable, it can do very dramatic loop-de-loops in the sky and then crash into the ground or into spectators or into cars. And we don't want that. We want to make sure we fly straight up in a beautiful straight line. And then deploy our parachutes at the top of the flight. So here are the instructions for downloading Openrocket. Again, this is also in the presentation. There can be some issues with Openrocket on Mac, but the wiki that's linked here gives a lot of info on how to get that properly installed. And they keep updating it, so my Openrocket might look a bit different than yours, but the general design idea should be the same. Now, moving forward. How do we go about designing and simulating a rocket in Openrocket? The process we're going to go through today is essentially starting by building the rocket from scratch. We'll start with the body tube, we'll add a motor, add a nose cone, add a parachute, add fins, and then most importantly, we'll adjust our stability and check our flight profile to make sure that the rocket flies the way it's supposed to. If this seems intimidating, don't worry, I'll walk you guys through every single step. It is really not that bad. And it's very rewarding when you do this right, and then your rocket flies the way it's supposed to. So, first step here is to add a body tube. This is just in the Openrocket file so that we can get started. So I'll head over to Openrocket and show you guys how to do that. Now, over here, we have our options for where to add things in Openrocket. This window over here will show you where your components go and how they connect together. Down here, once you add things, you'll see the diagram of your rocket with key information like the center of gravity and center of pressure. We'll get to that later. Over in this tab is where the motors are, and over in this tab is where the flight simulations are. Now there's nothing yet because I haven't added anything yet. So first I'm going to click on Sustainer up here, and then that'll let me add a body tube in here. So I'm actually going to skip this dialog box that opens up because I want to add custom body tube dimensions. And over here I'm going to add 34 inches long, outer diameter of 3.1 inches, and inner diameter of 3 inches. Material is cardboard, and that should be good to go. I click OK, and now we have a body tube. Now don't forget to save this just to make sure that you don't lose it. I'll save it like that, and then keep on moving. So that's our first step. We have a body tube. We have a body tube now, and now we need to make sure that the body tube can hold a motor. So if we head over to Motors and Configuration, and over here, click on Body Tube to make that a motor mount, now we'll be able to add a motor. There's another way to do this. It's by double-clicking on Body Tube, going to Motor here, and making sure this box is clicked here that says this component is a motor mount. That allows us to add a motor in there. Now, step 2 is to choose and add a motor. Now, first of all, choosing a motor can be confusing. We've tried to narrow it down to a couple, I believe 4 options that will simplify it for you guys. If we take a look at this slide here, these are the motor options we recommend. So they go from smallest to largest, and the only dimension that changes here is the length. The H133 is the shortest, and the H233 is the longest. Now, just for reference, the number after the letter is the amount of thrust that the motor puts out in newtons. So an H233 is going to have higher thrust than an H133, understandably. The power of a motor, the impulse of a motor, is the total energy it can impart to the rocket. That is not listed here, but it does roughly increase from left to right. If you're going for something you want to be really sure that you get it back, we recommend going for a small motor. If you want to go high and fast, I'd recommend going for a larger motor like the H233. But there's various trade-offs listed in here, and sort of take a look at them and choose which one of those seems most attractive to you. I used to choose my motors just based on color and thrust anyways, so I'm a big fan of the blue flames and also the red flames too. And yes, we ask that you don't select another motor unless you talk to one of us first. So definitely talk to the L1 lead or any other experienced members in the club, just to make sure that it's a motor that we have, that we can buy, and that's the right size for you. So, going back to choosing and adding a motor, we've already looked at the options. Now let's say we've chosen the H133. Let's go back over to Openrocket and add that in. So now we're over in Openrocket. We've gone up here, we've gone over to the Motors and Configuration tab, and what we're going to do is we're going to click New Configuration, and we're going to add our motor in here. So this giant list pops up. It can be a little intimidating. It has quite literally hundreds, if not thousands of motors, but in this box down here, it'll let us search. So if I hit H133, this motor will come up here. This Cesaroni Technology 163H133-14A. So that's the long official designation, but the H133 in the middle is what really matters. And as a sanity check, we can see that it's a 29mm diameter motor, which is exactly what we want in this case. So I'm going to go ahead and click on that. Now a number pops up here called ejection charge delay. All right, so what is ejection charge delay? Ejection charge delay is the period of time between when the motor runs out of fuel and when the ejection charge fires. The ejection charge is a small explosive charge at the front end of the motor that creates a lot of hot gas inside the rocket and pushes the parachute and nose cone out of the rocket so that the parachute can later deploy. Now we want this to happen at the highest point in the flight, which usually takes a little bit more than 11 seconds. And so we set it to 11 seconds to not mess up our simulations. And we can always adjust that later on. All right, so we're going to click OK, go on and save this again. I don't know why it's making me save it again, but there we go. All right, and now we're going to move on to the next step. So, that's why it didn't let me save it. So we now need to choose our nose cone. So if we go over here, there's a lot of different options to choose from. We need to choose our nose cone shape first. There are several options that Openrocket gives you. It gives you some explanation for all of them, If you don't want to worry about this, go ahead and just choose ogive. Ogive, I don't actually know how it's pronounced. But all these other nose cones have different benefits to their shapes. The only one I discourage you from is the conical. It looks not great, and it's optimized for high supersonic flight, which is not the regime that we're going to be going for. But if we look over here, so the steps for setting up your nose cone. So we're going to go back to Openrocket. And we'll go over here to the Rocket Design tab. Click on the body tube and click on nose cone. So we're going to ignore this massive box of options that pops up. We're going to go over here and adjust the length. So a length of 5.9 inches at the highest. This is so that we can fit it on the printers in NOLA Makerspace alongside with the nose cone shoulder as a single part. This makes it a lot easier. And we want the base diameter to be 3.1 so that it matches the outside of the rocket. Now you can choose and select your nose cone shape. There's a drop down here. Each option will give you a different explanation over there, but I'm going to go ahead with the ogive and just sit with that for now. Now the next thing we want to adjust is the nose cone shoulder. So this is the section of the nose cone that goes inside the body tube, and we want the diameter of that to be 3 inches and the length of that to be 1.97. This is what has worked for us well in the past, and this will essentially let your nose cone slot into your body tube. Finally, we want to override this mass of the nose cone to 150 grams. The reason we can't use Openrocket to calculate it automatically is because when we're 3D printing it, the lattice structure on the inside of the 3D print will mess up our calculations. So we're going to go ahead and hit OK, and oh no, what's this? Our nose cone's at the wrong end of the rocket. So to fix this, we'll go up here into the Rocket Design tab, click on nose cone, and drag it until it's above the body tube. And all of a sudden, it slots directly into place. So we'll go ahead and save that. And then it's on to the next step. So the next step is to set up a parachute. We use a standard 36-inch nylon parachute, but if you really want to use a different size chute that we have, we can do that. I will go through adding that in here. You should click on Mass Components, Parachute, and now this time we are actually going to use this giant pop-up list. We'll search LP-36, and this thing should pop up, and there's a 36-inch nylon chute. That's almost exactly what we're using now. But if we double-click on that, it opens up all the stats for that parachute automatically loaded in, so we have to do very little. The only things that we're going to adjust right now are the deployment. So right now it has it set to deploy at the highest point in the flight. That's not what we actually want. What we want is for the parachute to deploy a couple hundred feet above the ground. And the way we do this is with something called the Jolly Logic Chute Release. It's a small device with a barometer and an elastic band. We wrap it around the parachute, and it keeps the parachute sort of tied up in a bundle until the altimeter senses that it passes through a certain altitude on the way down. And then it opens, and then the parachute is able to open. And so we can program that to be different levels above the ground. But what we'll do is we'll set to be specific altitude during descent, and we'll set that to 300 feet. That should be more than enough for us. Now, finally, over here, we go to the Override tab. We'll override the mass to 160 grams. This is to take into account the shock cord and the attachments essentially that connect the parachute to the rocket. That way it's all in a single place, and we don't need to worry about that. Now, the other thing that I almost forgot to do is to move the position to the middle of the parent component and change this number here to 0, so that, as you can see, the parachute is now right in the middle there. Perfect. Now, if you want your parachute to look pretty, you can also make these numbers here 3 and 3, but there's no need to do that. It's just for cosmetics. All right, we'll hit OK. We'll save that. That is our parachute. And now the next step is to put in our fin assembly placeholder mass. So what is the fin assembly placeholder mass? It's a mass in the simulation that essentially simplifies what we do so that we have fewer things to code into the simulation, and just makes it easier to adjust later on once we actually build the fin assembly and weigh it. So we'll go back to our Openrocket. We'll click on the body tube, click on mass component over here. Come on, there we go. I'll rename it to fin assembly mass, just so I can know what it is. I'll change the mass to 250. We're going to set position relative to the bottom of the parent component and set this here to -4. Now, when I hit OK, this little dashed bubble should appear there. Now, be careful, because if you hit +4 instead of -4, let me show you what happens here. You hit 4, it'll still let me enter it, but it's moved it down out here outside the rocket. And so we don't want that. So I'll bring this back to zoom to fit. What I'll do is put it back to -4 where it's supposed to be. And this little dotted thing here shows us that we have our mass component in place. So I'll go ahead and save that. And now it's on to the fins. So back to the fins. First, we need to choose what fin shape we want. And I'll go to the next slide for more info because there's a couple options for that. The two main options we like to go with are trapezoidal or elliptical. Trapezoidal gives you lots of shape flexibility. It's really easy to translate into the CAD because these dimensions are clearly defined in Openrocket. And you have much better control over your center of pressure location, which, as I'll get into later, helps you adjust your stability a lot more. On the other hand, if you want to do an elliptical fin, it's the round fin. It looks really cool. It's aerodynamically efficient. Because we use a laser cutter to cut all the fins, it can also be cut just fine, but it is a little bit extra work in CAD to get that to work. And it's not as easy to adjust. The only requirements are these up here. You have to have at least 3 fins. Make sure your fins are not too small and not too long and thin. So we're going to go ahead and go back into Openrocket. We're going to go with a relatively standard trapezoidal fin shape. I'll click on that, and that'll automatically populate that with my 3 fins. So the fin cross section is set to square. That's good. Thickness is 0.118 inches. That's good. 3 millimeters. That's the wood commonly found in NOLA. I'm going to set the fillet radius over here to 0.25 inches. We'll have this from the epoxy connecting the fins to the body tube. Epoxy is kind of like glue. And then I'm going to adjust these parameters here just so it looks a little bit kind of like the shape I want. So let's see. Sweep length, I'll do 1.5. And so I have a nice, there we go. So those fins look kind of the way I want them to. I feel like that's a good fin shape. I'm going to go ahead and override the mass to 0 because the fin assembly mass that we already put in there, this little dash thing there, remember, already accounts for the mass of these fins. So we don't need to worry about that again. Now again, up in this tab, you can play around with any of these parameters besides fin cant. Please do not touch fin cant. It should be at 0. If you change fin cant to say 10, your fins will be angled and your rocket will spin wildly and then be out of control. So leave that at 0. Hit OK. And now the next step is to check on our fin shapes. So I'll give you some examples of good and bad fin shapes. Here we have some good fin shapes. We see these are good just because there's a relatively good balance between length and height. The length means there's a stronger way to attach it to the rocket. If we have fins that are too long and too thin, then it's a lot more dangerous, especially as the fins hit the ground first on landing. So what we see here is with this trapezoidal fin like that, I'll show you back in the Openrocket, when the rocket hits the ground, the bottom of the rocket will hit the ground first because the parachute is pulling up on this end of the rocket. So when this end of the rocket hits the ground, we want to make sure the fins don't also hit the ground because if they do, they'll absorb all the force of the rocket hitting the ground and they'll probably break. And if a fin breaks on landing, you don't get certified. You'd have to build another rocket and try again. We don't want that. So that's why we want this nice trapezoidal shape. We get the same advantage from a rounded shape, but again, it's important to have good balance between the root chord, this length here along the rocket, and the height, so it's not too tall and thin. Now for some examples of bad fins, this fin here extends way beyond the end of the rocket. I've flown fins like this myself, and I've had some success and lots of failures. So if this fin point hits the ground first, all of the load will go through this skinny section here, and it'll just snap right off. It will make your rocket go faster, but please do not create fins like this. It is very tempting, but it is not worth it. And then over here is an example of a bad elliptical fin that's just too tall. There's too many aerodynamic forces at the tip, and not enough area for it to properly attach. And again, it can break during a hard landing. So that's okay. I'm going to go back to my fin shape. I'm happy with that. So the next step now is to adjust the stability. This is perhaps the most important part of designing the rocket. It has to be stable or it will not be allowed to fly, first of all. And if you were to launch it, it would just do loop-de-loops and crash into the ground. And that's obviously terrible and we don't want that. So what we want for stability is we want our center of gravity to be forward of the center of pressure. Now what that means is we want the center of gravity, this little blue dot, to be closer to the nose than the center of pressure. Openrocket conveniently tells you the stability up in the top right corner of this window here. And oh no, my stability is negative. What could I possibly do? Sorry, there's two good ways to adjust the stability because it depends on the location of your center of pressure and your center of gravity. You can either adjust the center of pressure or adjust the center of gravity. So we're going to start by adjusting the center of pressure. This is the aerodynamic approach. As a little bit of background, the center of pressure is where all of the aerodynamic forces act on the vehicle as a point. So if you can think about it as if the rocket were a cardboard cutout where it would balance on your finger. So moving fins further back, making bigger fins will move your center of pressure further back and vice versa. So the first thing to do is if your stability is below this 1.5 minimum range is just to make your fins bigger. And we want to do this in a reasonable way, but I'm going to go ahead and increase my height here. I'm going to increase my root chord a little. Let's do that. Increase the tip chord to, let's say 4. And now, so those fins look pretty, and I'm happy with how they look, and they're good, they're stable, they're safe. Maybe I'll make them a little bit more swept. But I'm still not all the way there. So there's more things I can do. I can adjust the shape of the nose cone. I can play around with the fins to have bigger fins, to have more swept back fins. But in this case, I'm actually going to take another approach. So because stability is defined by center of gravity and center of pressure, we can adjust either one separately or both in conjunction. So what I'm going to do in this case is I'm going to increase my nose cone mass to make my rocket more stable. So we'll go over here. We've already overridden it to 150, but I'm going to say I want it to be 250. And that has gotten me pretty close. So I'll say, let's go with 270. And perfect. There we go. Now my rocket is above that 1.2 stability margin. And the way we'll get that extra mass in the nose cone is just by 3D printing it with a higher level of infill. Now you can always adjust your motor to affect your stability, but again, the recommended ways to do it are to reduce your nose cone mass, or to make your fins bigger or less swept. So here's an example of a good open rocket design. This is quite similar to my own, but as you can see, there's a good fin assembly placeholder mass kind of just ahead of the fins here. There's a motor in here. We have nice shaped fins that are not too small, not too big. They're trapezoidal, so they will be less likely to break on landing. We have a parachute about in the middle of the rocket. Then up here we have a nose cone with a nose cone shoulder. The altitude is nice and high. The stability is above 1.5. Center of gravity is ahead of the center of pressure. And that is wonderful. And you can see over here, I have just about the same thing. The reason my apogee is a lot lower, apogee's max altitude, is just because my motor is smaller and weaker. So once your rocket is stable, you can play around with certain parameters to say, make your rocket go higher, make it go faster, make it, try and break the sound barrier if you want. That might be a bit difficult, but you can try. And so you can play around with different areas of your design to do that. You can make your fins, you can experiment with your fins. You can make them smaller, larger, sharper, pointier, anything you want. as long as you remain stable. Now, if you don't remain stable, you should go back and play around with the nose cone mass, play around with the fin shape, with the nose cone shape, or even shorten the body tube to make sure your rocket remains stable at the end. So once you've optimized, let's say I'm happy with this simulation, it's going high enough, I don't want to risk it too much. I want to make sure it actually flies smoothly. So the best way to do this is to go to the Flight Simulations tab. This is where all your simulations live. This is how you'll check on your numbers. Now, I want my simulations to run automatically, so I like to go to Edit, Preferences, and go Simulation, and click this Run Out-of-Dated Simulations when you open the Simulations tab. It's just convenient. It helps you a lot. But I'm going to edit a few things before I run the simulation and plot everything just to double check. First of all, edit the length of the launch rail to 7 feet. So make sure this is 7 feet and not 7 inches. And then once that's all set, I can click OK. Now just double check, run this and double check that all these parameters seem vaguely reasonable. The key one I want you to look at here is your off-rod velocity. So this needs to be above 50 feet per second. In my case, it's 80.9. If your off-rod velocity is below 50 feet per second, you need to choose a motor with higher thrust. The reason for this is so that when your rocket lifts off the rail, if it is too slow, a gust of wind could hit it, knock it sideways, and then shoot it off into the distance, and that is not what we want. So just double, triple check that. Now, once we're happy with that, click on your simulation, click plot, and then make sure you're plotting vertical motion versus time. And you should get this very nice graph here. So it'll look relatively similar on your end. You should see the altitude curve going up nice and smoothly up to the apogee, which is the highest point, then a relatively smooth line down. And then as the parachute deploys close to landing, your rocket should go a little bit more slowly before hitting the ground. And it's really important to have a smooth altitude curve and also a smooth velocity curve. So this orange curve here. Be aware that the orange and the yellow colors can sometimes switch for whatever reason. So this is an example of a good flight profile. I will show you guys an example of a bad one real quick. That would be this one right here. So as you can see here, we have a very low apogee. We have negative acceleration during the burn, which means the rocket has done a somersault and is essentially firing backwards. And we see lots of other oddities listed on here. So make sure that your simulation looks more like this than like this. I'll go back to my simulation over here. All right, and now it's time to review your design and submit your paperwork. So first of all, export this as an image or just take a screenshot of it so you have it. If not, you can run it again later on. But let me go through the checklist here. So starting from the top, our design has a 3-inch inner diameter, 3.1-inch outer diameter body tube. That is 3-inch inner diameter, sorry, 3.1-inch outer, 3-inch inner. That is perfect. We have 3 fins. We have a nose cone. The base diameter of the nose cone is 3.1 inches. That's perfect. Fin mass has been overridden to 0. It'll show up down there. If it hasn't been, again, go to the override tab, click override mass and enter 0 in that box right there. Fin shape and thickness are acceptable. So again, we've compared that to those slides. We'll double check the thickness is 0.118 inches. That's perfect. The nose cone mass is between 100 grams and 454 grams. It's overridden to 270. That's perfect. There is a 250-gram mass, 4 inches in the bottom of the rocket. That's our fin assembly placeholder mass. We have that in there. It's overridden to 250. That is fantastic. We have the 36-inch diameter parachute right in the middle of the rocket. The stability is between 1.5 and 4.5. We're at 1.52. That's amazing. Our off-rod velocity is over 50 feet per second, and our vertical flight profile graph looks good. So that's incredible. We're done with our design already. The next step is to export this design to make sure we have the paperwork done for that, and to move on to actually modeling the rocket in CAD, which is computer-aided design, 3D modeling. Before you leave this tab, if you want to play around with how high your rocket flies, how fast your rocket flies. You can always try out adding different motors. So in this case, I'm going to try out adding an H140 in here as well. So I'll go an H140, change the delay to 11. Okay. And I'll see that I go a lot higher with that H140. But be aware that when you change your motor, your stability can also be affected a little bit. So try and make sure that your stability works with any motor that you could possibly fly on. But in this case, I want to swap back to the H133, so I'll just change the configuration in there. And if I wanted to run a simulation, I'd go back over here and run it. But in this case, I don't exactly want to. All right, so it's time to print out the design report. We go to File, Print Design Info, and then everything besides the design report gets unchecked. And I'll show you guys what that looks like. So you should have something like this, has a diagram of your rocket, and for every motor, it'll show a bunch of things here. Now, this is important because we need to know this number, the optimum delay, when we go to the launch site. Every motor comes with a set delay charge. So usually it's this little number right here after the dash, dash 14, dash 11 right here. This means that the H140 has a delay charge of 11 seconds and the H133 has a delay charge of 14. Now, when we get to the launch site, we're going to need to sort of physically shave down the delay grain, the explosive charge itself, so that it goes from 14 seconds to 9 seconds worth of fuel. We have a special tool for that. It's really easy. We'll show you. But it's important to know this number here, how long the optimum delay is expected to be. And that is that. Thank you very much for bearing with me in this hopefully not too confusing Openrocket demo. As always, stay tuned. Reach out to experienced members of the club for any questions. Reach out to me personally, or just keep following the slides. Next step will be to model your rocket, and then after that, we'll get to start building. So that's it for me today. Thank you.